Okay, here we are looking at this particular question about nucleophilic substitution. So remember nucleophilic substitution, I have two types of mechanisms, right? SN1 and SN2. SN1 is unimolecular nucleophilic substitution, and SN2 is bimolecular nucleophilic substitution. I am not going to go through in depth the construction of the mechanisms because that should be second nature to you by now. But I've written them down a bit just underneath this, although I'm not going to scroll down and show you yet. Sorry. Okay, anyway, now let us look at the first part of this question where they ask you to predict the dominance mechanism and explain your reasoning. Okay, so now we are going on to explanation questions about the mechanisms. Okay, please do not be confused by questions on this. I think we actually did a lot of these explanation type questions last year, right? Like you remember last year we did a lot of questions on like uh when we were doing electrophilic addition in alkenes, we considered a lot of things like, oh, um why is what did we consider again? The things about does the product mixture rotate plane polarized like why or why not? And then we had all those ideas about the racemic mixture, things like that. And then also remember we also had Markovnikov's rule in alkenes to predict the major product. But ultimately, I think I've mentioned before that it is best not to memorize Markovnikov's rule blindly. You can instead use very intuitive ideas about radical or in this case carbocation stability to predict the major product based on the relative stabilities of the carbocation intermediates that can be formed. Okay, so now we are going to do another explanation type question based on the mechanism about predicting the dominant mechanism for these two. Now, the first step, of course, is to draw them correctly. So let's look at 1-bromobutane, right? Let's draw that together. Butane, 4 carbons, 1, 2, 3, 4, and then 1 bromo. So this is 1-bromobutane, and obviously this is going to be a primary halogenoalkane. Okay, next 2-bromo, 2-methyl-propane. Propane, right? 1, 2, 3. Then at carbon 2, I have 1 methyl, I have 1 bromo. So obviously, what type of halogenoalkane is this? This is a tertiary halogenoalkane. And we know, based on theory from our lecture notes, that usually your primary halogenoalkanes are going to react via SN2, and your tertiary halogenoalkanes are going to react via SN1. I think that is yeah, this particular bolded point here. But I do not like the way that they have explained it here, because ultimately, right, there's a steric and there's an electronic factor for both. But I feel that ultimately, right, when you are explaining why it reacts via SN1, you should talk about the electronic factor. And when you are talking about why it reacts via SN2, you should talk about the steric factor. So obviously, if I have 1-bromobutane, actually no, I'm not going to draw it in skeletal. This is one of the mechanisms, right, that you are highly encouraged not to draw in skeletal, because you especially for SN2, you need to show the stereochemical inversions. Okay, so all the other mechanisms are your FRS, EA, electrophilic substitution, nucleophilic addition, you can draw in skeletal. Nucleophilic substitution, okay, both SN1 and SN2 are the ones that I do not recommend you draw in skeletal, and you cannot draw in skeletal for SN2 because the stereochemistry you have to show. Okay, so let us draw this. We don't need to expand every bond, of course. We can just write this as CH2, CH2, CH3. And then this is Br. So, obviously, this is a primary Rx. And what do you notice? How many alkyl groups do I have? This is just one alkyl group. And I said in the video, I think, on acidity, that you cannot just say alkyl group. You must say what kind of alkyl group. So this is one propyl group, 3 carbons propyl. And this alkyl group contributes to steric hindrance. But this is only one alkyl group. On the other hand, let's draw our tertiary halogenal alkane. So that's going to be, let's draw our chain first, right? 3 carbon chain. And then I have, at this carbon 2, I have 1 methyl, I have 1 bromo. This one, I have 3 alkyl groups. 3 methyl groups. So therefore, am I going to have more steric hindrance here or less? Obviously, I'm going to have more steric hindrance. And that is why, remember, our SN2 mechanisms involves what we call a backside attack by the attacking nucleophile. So the attacking nucleophile is going to come somewhere here. Okay, let's say it's OH. It's going to start here. It's going to attack this delta plus carbon. And then this one comes in. This one goes out. And of course, you have your transition state. So this one is obviously less steric hindrance as compared to this one more steric hindrance. That is why the dominant mechanism for the reaction of 1 bromobutane is going to be SN2. Bimolecular. And why is it called bimolecular? Because it's one step. So in the RDS, in the rate determining step, how many molecular species do I have? 1, 2. That's why bimolecular. Okay? And therefore, this one is obviously going to be SN1. So that's about the steric factor, right? Now let me explain the electronic factor for SN1. Remember, my SN1 mechanism involves the formation of a carbocation ion intermediate. So how do I form this carbocation ion? I have delta plus, delta minus. This one will go away. There is no attack. This one just goes away on its own, okay? That's why it's a slow step. And so I will be left with only 3 groups. So this carbocation ion is trigonal planar. And I label the delta plus carbon with a plus charge because this is a carbocation ion. Now, we know what is the property of alkyl groups. They are electron donating. So obviously, we are very familiar with this idea from alkenes when we were doing electrophilic addition, that a tertiary carbocation ion is much more stable because it has 3 alkyl groups to donate electron density to the electron deficient carbon atom, and therefore this will actually disperse the positive charge. Okay, so these 3 electron donating methyl groups will also disperse the positive charge on the electron deficient carbon to a greater extent. And therefore, this tertiary carbocation ion is much more stable as compared to the primary carbocation ion that would be formed if this were to undergo SN1. And that is why the dominant mechanism for 2-bromo-2-methylpropane is SN1. So yeah, these are just the mechanisms. Just remember, right, for SN2 mechanism, bimolecular nucleophilic substitution, or you can also write nucleophilic substitution and then bracket SN2. This is also valid. Okay? And then for your unimolecular nucleophilic substitution, it's just this one. This is the tertiary carbocation ion that I was talking about. Now, just a small extension, right? This particular tertiary carbocation ion here, what do you notice? It is trigonal planar. It has trigonal planar geometry with respect to the electron deficient carbon atom. So you notice, right? The bromine nucleophile can actually attack. No. So sorry. The OH minus nucleophile can actually attack this from either the top or the bottom of the plane with equal probability. But question we are familiar with this line of reasoning, as I said earlier, when we are talking about chiral or racemic product mixtures from electrophilic addition. But is this carbon chiral? No, right? Because I have 3 alkyl groups. But then I 举一反三 a bit, I changed the question. What if the tertiary carbocation ion that I'm interested in is this? Wait, sorry. Let's make this 3 carbon. Okay, so let's make this a propyl group. This is my central carbon. Let's make this a methyl group, and then this one a ethyl group. And then I have this Br. Now, is this carbon chiral? Yes. So, my carbocation ion is going to be like that. And then, yeah, like that. So this is my carbocation ion. And then when my OH nucleophile attacks this, my OH minus now can attack from either the top or the bottom of the plane with equal probability. So this is going to be my fast step, and I am going to form basically just this thing, but replace with OH. So it's going to look like that. We are just erase some things, and then this is now OH. And obviously this carbon is chiral, so therefore both enantiomers of this particular product are going to be formed in equimolar amounts, and and their effects on the rotation of plane polarized light will cancel each other, such that I get a racemic product mixture, and the product mixture is not optically active or does not rotate plane polarized light. So please ensure, don't get too excited. Make sure that your carbon is chiral before you jump to these kinds of conclusions, okay? But I'm just showing you as a means of comparison between the mechanisms based on ideas that you have learned, how we can explain some things using logic that we have learned from earlier. Okay, I don't think I need to go through the mechanisms in depth, but just remember, right, for your SN2, just remember, label the transition state, have your partial bonds, label this negative charge on the transition state. Okay? I think that's it for this particular question. Yeah, so I've shown you the explanation, I've shown you the mechanisms, I've gone to a bit of extension, and I think that is enough for now. Next one, we are going to look at this particular one. So it is also about acidity, but it's slightly different. So I think that will be in a video. I'm going to put it in the hydroxy compounds folder. So together in the same folder with the previous acidity video.